Good day guys, welcome back to Wiki Science YouTube channel. In this video we'll be talking about rectification, half-wave rectifier. We solve some questions on half-wave rectifier. We give the waveform of half-wave rectifier, and in a bit of time we also consider some review or basic aspect of the full-wave rectifier, even though we won't go deep into aspect of full-wave rectifier. Let's get started. What is rectification? Rectification simply means you're converting AC to DC. That is, you're allowing current to flow in one particular direction. So you are converting AC to DC. So we say rectification is the conversion of AC to a positive DC. Do not forget that what we use as a rectifier in this sense is called diode. So we are using diode as a rectifier. And in the previous video which we've watched, the symbol for diode is this, right? This is the symbol for diode. Let's make a review quickly. And we have this to be a diode in the circuit. For proper understanding, I'll present to you this way. Okay, now this the same diode that you have here. Do not be confused. Is what you have here. But in this case now we have it to be P and you have it to be what? N. That's P-N junction. So now I want to quickly look at the concept of biasing to understand better what we mean by rectification now. So now here will be our positive plate of the voltage source, which is our DC, and this plate will be our negative voltage. And do not forget, what do we call this aspect? This part is called, this region is called what? The P-N junction. And there is a particular energy that must be overcome in this region. What do you call that energy? The energy is called what? The energy barrier. So we must overcome this energy called what? Energy barrier. This place is positive. This place is positive. There will be repulsion. And as there is repulsion, there will be movement of what? There will be movement of charge carrier towards the P-N junction. There will be movement towards the P-N junction. And electrons here, you also have negative. There will be repulsion. So repulsion will occur here. You also have repulsion here. So as there is definitely repulsion on both sides, it will cause the electron now to move across the what? Across the P-N junction and occupy this region. This region now is leveled, and as a result of that, current can simply what? Flow. As a result of that, current can what? Current can rapidly what? Flow. The reason current flows here is because the electron jump into the what? Into the P-N junction, and it reduces the energy barrier. And as it reduces the energy barrier, they can allow current to flow through. So this is what we refer to as biasing of diode. For current to flow through in this region, when current flows through, we call it a what? Forward bias. Forward bias. But if current does not flow through, when do we have a case whereby current does not flow through? That is when the diode is connected this way, in which this space will remain your P-N junction. This is your P and this is your N. In this case now, we now have this particular voltage source to be connected this way. We interchange the terminal. So here now you have the negative and here you have the positive. You can see what we did here now. We interchange the terminal. This is positive, this is negative. So what do we have like this? Because this place is positive, right? And this place is what? Negative. With very repulsion, never. What do you have there? Attraction. And what do you think happens here? the attraction will cause this particular charge carriers to flow in the direction of attraction. And what do you think happens? It will cause this PN junction to increase in size. Then they have a new what? A new length. In this case now, they migrate from this length towards the other end. The same thing occurs in the other side. On the other side, we have attraction to also occur. When attraction occurs, the charge carriers migrate towards the side of attraction. As they migrate towards the side of attraction, a new region for the charge carrier is formed. And as the new region is formed, this particular aspect what disappear. And what do you have? You can see that this space that we have has become increased. The increased space in between them, this increased space will prevent current from flowing. It will prevent current from flowing. But this does not mean that the current flow, the current across this diode is zero. Never. It does not mean that the current is zero, but it is approximately zero. It is not zero, but approximately zero. The reason why I say to be approximately zero is because there are cases in which the electrons can actually dissociate and recombine. When they dissociate and recombine, let's assume that we have one electron to have dissociated and jump to this region. As this electron jump to this region, and you have a what? A conducting region here, it will cause this particular region to allow current to be carried by this electron, this minimum electron, to flow across this diode. And once that occurs, the current produced will be very low, approximately zero, but not zero. You already know why it's not zero, because it can occur even if you have 10 disciples. You cannot have all the 10 disciples to be what? To be one, as you always have what? One, that which will what? Will be Judas. So the same thing happens here. The electron here can actually dissociate and jump towards this region and cause the electron to flow. So it will not make the current to be absolutely zero. Okay, another thing we want to explain further here is that as this occurs, such that the charge carriers, they are separating totally from what? PN junction, causing the PN junction to become widened up. Something can be developed here. We call it the breakdown voltage. We call it breakdown voltage. What is breakdown voltage? Breakdown voltage is the voltage across an insulator. You know, this will become an insulator now because current is not flowing. This will be said to be an insulator. Breakdown voltage is the voltage across an insulator which makes the insulator to become conductive. The minimum voltage across the insulator that makes the insulator to become what? Conductive is called the breakdown voltage. How do we know that breakdown voltage can occur here? Now, as this positive end attracts the what? The negative terminal. Remember the third law of motion, that for every action there's always equal and opposite what? Reaction. There can be a reaction here. And what's that reaction? The reaction that which, while the attraction is going on, they can react. It will now cause the current to flow in opposite direction. You can see that the direction of voltage is towards the what? Side of attraction. But now when there is repulsion due to breakdown voltage, they will repel from each other. When they repel from each other, current will now flow massively in this direction. When current flow massively, like in the opposite direction, current will be forced across the PN junction, and it can destroy the diode immediately. That's why we call it breakdown. So it can cause damage to this diode. Let's now come back to what we refer to as rectification. So this covers the aspect of review. Let's quickly come back to half-wave rectification. Now, what is half-wave rectification? What differentiates rectification from biasing? What differentiates rectification from biasing is that in a biasing we use DC, but rectification we use AC. We're using AC for rectification. Let's try to understand what we're explaining here. Now, if I'm using AC instead of a DC, I can have something like this. The symbol for diode, and you have a load here probably. Now let's check the voltage source. Now, when you see this in an electric circuit, this symbol, it simply represents AC and not DC. What is AC? An alternating current is called AC. An alternating current is a current that changes its direction periodically. When you say periodically, that is intermittently or sinusoidally. Now let's see. Remember that we have what we refer to as cardinals in space. What are those cardinals? You can have the X cardinal, we can have the Y cardinal. One thing you observe in this cardinal plate is that this side of Y is what? Positive, and this side of Y is what? Negative. Meaning that when I'm moving upward in a phase, I have what? The positive sign. When I'm moving downward, I have the what? Negative sign. Now, when I say something changes its direction periodically, it means that as it moves upward, so does it reverse downward. That's what we mean by sinusoidal, like reversible. So it moves up and comes down rapidly, meaning that it covers the positive and the negative words and the negative signs. The same thing happens on the other side. If this side is positive of X, this side will be what? Negative of X. As it moves towards the positive of X, when it turns back in the other direction, what will it do? It will move towards the negative of X. Meaning it's covering the negative end and it's covering the positive end. Or it's covering the positive end and it's covering the negative end. That's what we mean by alternating. Now here, there are two-wave cycle. We call it the first half cycle, and the second is second half cycle. This first half cycle is also known as the positive half cycle, and this other one is called the negative half cycle. Why is it so important to know? You'll get to understand now. Meaning that as this sine wave as this AC is used here, it will be having the positive half cycle and it will be having the negative half cycle. In the positive half cycle, we use this terminal as a positive end, and this terminal will be the what? Negative end. In the second half cycle, we then interchange that this one will be our negative terminal, while this will be our positive terminal. Let's see something now. So now, in the first half cycle, for AC, in the first half cycle, we're using this as a positive. Don't forget that the current here we have a load now. Here we have a diode, and this is our diode. But for you to understand better, I'll change this diode sign to normal PN diode, so it will be this way, like this. This will be our P and this will be our N. We have the load here and you have something like this. Don't forget, this N9 is the positive, this is the negative. We call this positive half cycle. So this is the positive half cycle in which we have this terminal to be the positive. Now, if this terminal is positive, you really understand what we're trying to explain now, that if this place is positive and this place is positive, what will occur? Repulsion. And when repulsion occurs here, the electrons jump to fill the what? The p-n junction. And as they fill the p-n junction, what happens? They fill the p-n junction because of what? Repulsion. So this one will repel this one, and the what? Current flows. And as current flows, it will flow across the what? Across the what? The resistor. So now it means that the current input into the what? Diode. The current that flows across the diode is the input voltage, and the current that which we have across the load will be what? Output voltage. In the first half cycle, your input voltage will consequently produce a what? It will produce an output voltage, and this is it. Okay, let's now consider the second half cycle. In the second half cycle, we take the same kind of symbol here. We take the same symbol here, and we consider the same symbol. If this end is positive in the first half cycle, what will it be now? Negative. So here, it simply means that this place is positive, this place is what? Negative. This is our what? Resistor. Let's present it in a more in a way that can be comprehended better. So we have something like this. So here, this is our P and this is our N. What do we call this junction? The P-N junction. So now the input voltage, now let's see what happens here. This side is negative, this side is negative, and this side is what? Positive. In the second half, this is the first half, and this is the what? Second half. In the second half, this side is negative, this side is positive. What do you think happens? Attraction. And once there is attraction, what happens to the space? It widens up. And when it's widening up, it moves towards the what? Side of attraction. As it moves towards side of attraction, will there be current flowing through? No. So here, no current is flowing through. Here, will there be any voltage recorded? No. So it means that the output voltage here is 0. In the second half cycle, the output voltage is 0. But in the first half cycle, the output voltage is significant. So now, I can simply say that the net voltage produced by AC. So this is the AC voltage. This is the AC voltage. Now the AC voltage that is produced here in the first half cycle will be V0, which is the maximum what? Output voltage for the first half cycle, plus the one you get for the what? Second half cycle. Let's just put it as V2. Our V2 here now, second half cycle, is what? 0. So I will say the voltage that I record when alternating current is produced across a diode will be what? Will be for the first half cycle alone. It will be for the first half cycle alone. So here, in the first half cycle, you say current flows and voltage, current flows, voltage registered. In the second half cycle, current does not flow, voltage equals 0. That is, the voltage is 0. Now when current flows, what do we call it? Forward bias. So it means that the first half cycle of AC cycle is a forward bias, and the second half cycle is a what? Is a reverse bias. Is a reverse bias. The second half cycle will be a what? A reverse bias. It will be a reverse bias. So let's get the waveform of this now. To get the waveform of this, we'll be using this further in an equation, and in that equation it will show the average potential that is registered across the load. The average potential registered across the load will now be the average of the total what? The total cycle. And what do we have for the total cycle? You know, you have the first half cycle and we have the what? Second half cycle. In the first half cycle, voltage flows. In the second half cycle, voltage does not flow. So if a complete cycle is what? 360. In the first half cycle, what? 180. The second half cycle will be another what? 180. That's the reason we always have the average voltage now to be the peak voltage. What do you mean by peak? The maximum voltage that is generated from AC over the what? Pi. And don't forget, pi in radian is equal to what? 180 degrees. But here now, it has been resolved from radian. And that is the reason we use pi as 3.142. So here, we use this V naught as what? As the peak voltage. What is peak? Peak is the maximum voltage that is recorded. So this is the maximum voltage recorded. Let's see the waveform quickly. Let's see the waveform. Let's see the waveform. In the waveform, this is what you now have. In the waveform, we already know that alternating circuit is having two what? Is having two cycles. The upward and the downward. The upward and the downward. The upward and the downward. And it continues like that. For the first half cycle, current flows in the positive direction. Current flows in the positive direction. You know, upward is positive, downward is negative. In the negative half cycle, current does not flow at all. That's the reason we're having this straight line. Current does not flow at all. When we now combine the two together, when we combine this first half cycle and the second half cycle, what will now be shown will be something like this, like this, like this, like this, like this. Meaning that we only have the peak and the zero. The peak voltage and the zero. The peak voltage and the zero. These are the two types of voltage that you can ever register in half-wave rectifier. These are the two types of voltage you can register in half-wave. Okay, now to understand something clearly here, you realize that we say in the second half cycle, voltage does not flow. It then means that the voltage you have in the second half cycle, which is said to be what? Zero, that does not flow. That voltage is called the peak inverse voltage. It is called the peak inverse voltage, PIV. You know, this is for the first half cycle and this is second half cycle. And we said that V2 here is equal to what? 0. So it means that this V2 we have, which is the voltage for the second half cycle, is the peak inverse voltage. The peak inverse voltage. This is the waveform. So we have covered the aspect of waveform. Let's quickly look at the introductory aspects to AC circuits. We just want to derive some equation here that will be used in our further calculation. Okay. In AC, the waveform of AC circuit is actually represented with V equals V naught sine omega t. This V is called instantaneous voltage. Instantaneous voltage. What is instantaneous voltage? The voltage measured at the instant of time is your instantaneous voltage. V naught is your peak voltage, or you call it amplitude of voltage. Amplitude of voltage, or you call it the maximum voltage. That is the voltage that is generated. The maximum voltage generated is your maximum voltage. Now, something you need to understand here, that this instantaneous voltage becomes your root mean square voltage whenever the phase angle is equal to 45 degrees. This instantaneous voltage becomes your root mean square. So here now, your root mean square equals V naught. You can see that I'm not writing ordinary V again. I'm writing root mean square because I'm about to write sine 45 degree here. This omega t is taking 45 degree. At 45 degree, at phase angle of 45 degree, your instantaneous voltage becomes your root mean square voltage. On the other hand, I can say my root mean square voltage is equal to what? V naught over what? Square root of 2. So our V naught, which is produced, don't forget, this is our V naught. The V naught produced is equal to what? What's V naught produced? The V naught produced will be what? The root mean square voltage times root 2. Why am I giving you this equation? We want to use this equation to calculate the what? To calculate the amplitude of voltage. Because in AC circuits, when you have AC circuits, in AC circuits, the voltage produced is always the root mean square voltage. In this AC circuit, the voltage that will be produced here will be your what? Root mean square voltage. So if your root mean square voltage is produced here, I can calculate the what? I can calculate the maximum voltage across the diode using this formula. And how do I get the maximum voltage? I'll just say your root mean square times what? Root of 2. And how do I now get the average what? Voltage across the diode? The average voltage across the diode will be what? Divided by what? Pi. When you divide it by pi, you get your what? The average voltage. Okay, let's solve one question here. Okay, let's take this question for example. A 50 ohm load resistance. So this resistance here now is said to be 50 ohm. Is connected across a half-wave rectifier. The input supply of voltage is what? 230 root mean square. Don't forget I told you that the voltage produced by the source is always the root mean square. Here now is said to be what? 230 volts. And the frequency is at 50 Hz. The frequency is at 50 Hz. We are to determine the output voltage. How do we determine output voltage? Don't forget, the output voltage is this, which is the average voltage. That is the peak voltage over what? Pi. So we have to get the peak voltage. How do we get peak voltage? Remember, I've given you a formula that your peak voltage is equal to your root mean square voltage times root 2. So what is our root mean square? 230. And this is times root 2. When you multiply these two together, what do we get? Multiply the two together. So now we have 325.3 volts. This is our what? This is our peak voltage, but not the what? The output voltage. How do you get the output voltage? Our output voltage will be said to be this is your output voltage. You have to be V naught over pi. V naught over pi. And what's our V naught? 325.3 divided by 3.142. Because pi is 3.142. Okay. Now let's divide. Now when you divide, we have something like 103.5 volts as our average voltage, which is our output voltage. So that is our output voltage. Now here we are asked to get the peak to peak ripple. Remember that when I gave the sum total of voltage waveform of voltage, I said in the first half cycle there is a peak voltage produced, but in the second half cycle no voltage was registered. Let me use another marker so that we can understand. We have in the first half cycle voltage was registered. In the second half cycle no voltage was registered. And in the second half cycle voltage was registered. This is what we refer to as the peak to peak. This is from peak to peak. So now what is the peak to peak? It means the maximum peak to the what? To the zero. So what do we have? The maximum peak to what? To zero. So we have it to be, that is voltage is equal to, that is your maximum voltage plus what? The maximum voltage plus your what? Your second voltage. And you don't forget that voltage in the second half cycle is always what? Zero. So we have it to be, what's our maximum voltage? The maximum voltage produced is what? 325.3 plus what is the voltage produced in the second half cycle? 0. So the peak to peak is 325.3 volts. This is our answer. This is the peak to peak voltage. Now let's get the percentage output. Percentage output waveform. The percentage output waveform is equal to your output voltage over your input voltage. Since percentage is what we're talking about, we express in terms of what? 100. So now here, what's our output? Don't forget our output is what? 325.3. But the voltage developed in the what? The voltage supplied, which is the input voltage supplied, is what? 103.5. The input voltage of the AC is 103.5. Don't forget, this is coming from the AC, and this is coming from the what? This is going to the what? Is going to the load. So here you have times 100 times 100, and what do you get here? 314%. You can see that the percentage output here, the percentage output people here is very, very high, is over 100%. Yes, this is what it means. It therefore means that your AC has been converted to your DC. But in this sense, some components or major component of your AC has actually flow along. And this component can be removed by applying shunt to this your load. And what shunt? Shunt means it's going to deviate maximum what? Current from your what? From your load. So that the wanted or the specific amount of current required by what? By your load is diverted to this region. Is sufficiently supplied. What are we talking about? We're simply talking about filter circuits. This is done in a filter circuit. So filter circuit helps to remove the unwanted component of your AC from your DC supply. So that is what we're talking about, the filter circuit here. So a filter circuit will be required in this region so that the specific or wanted amount of your voltage is actually supplied to your load. So now we want to quickly check the view on a brief review on the full wave rectifier. In a full wave rectifier, this is what is done. In a full wave rectifier, you have two particular diodes to be used. We have two diodes to be used here. There is coming, the voltage source is your AC, but here now we have two diodes. So now see, don't forget in the first half cycle, there are two half cycles of your AC. In the first half cycle, you have one terminal to be positive and this end will be what? Negative. And this place is positive, right? And this place is what? Negative. Are we together now? So what happens here? This place is what? Positive. This place is what? Negative, right? And this is your what? This is your load. Now here, the positive and positive will what? They will repel. And when positive and positive repel, current flow to this region, right? And what do we call this? Forward bias. And this current flows across the resistor. During the same cycle, this one is negative, this place is what? Positive. What happens here? There will be attraction. Will there be flow of current? No current. Right? And what do we call this cycle? We call it a what? A reverse bias. So here now, this is serving as a forward bias, this is serving as a reverse bias. When we now go to the second half cycle, in the second half cycle, we interchange the sine wave. So here, this place will become negative and this place will become what? Positive. So in the second half cycle, what happens? Positive and positive, there will be what now? Repulsion. And once there is repulsion, what happens now? Current flows. And once current flows, what do you call it? Forward bias. What happens here? This place will become positive and negative. It will become what? Attraction. And once attraction comes in here, no current. And once there is no current, what does it change to now? It will change from a forward bias to what? Reverse bias. Why this one changes from what? From a reverse bias to a what? A forward bias. In a nutshell, during the first half cycle, current is flowing across the load. During the second half cycle, current is yet still flowing across the load. Then look at the waveform. The waveform of AC will be given this way, right? This is this for waveform. But for the first half cycle, current flows like this. Current flows like this. For the first half cycle. In the second half cycle, current flows this way, this way. So it means that when you now sum the first and the second, how do you now have the wave? The wave will be represented this way, this way, this way, this way. This is for your full wave rectifier, meaning that the current is flowing in the two cycles of the alternating cycle. That's why I call it a full wave. But in half wave, current is only flowing in the first half cycle, while in the second half cycle, no current is flowing. Thank you.